Crypto3. Okay. All right. Hello, everybody. Welcome to Crypto. So this is secure protocol design. This is actually, I think, one of the most important embedded team meetings. And I would say like this is actually applicable well beyond embedded systems. Like any kind of secure system that you have is probably going to involve some form of cryptographic protocols. So like websites like TLS, HTTPS, all of that stuff. You can have cryptographic protocols being used in like other kinds of areas in application software and like operating system related stuff, like everywhere. Secure boot. This is a topic that's I think very kind of fundamental to just security as a whole. So I guess before we actually start with the kind of techniques for how to design protocols and how to analyze them, like we're going to think about what kind of situation are we in, right? Like it's very important when we are in when we are doing security of any sort to like know what actual like model are we in, what kind of system are we trying to secure. We need to know what security properties do we actually want from this, and we need to know what is our threat model. So like if you don't know these things, then it's actually not very easy or useful to come up with any kind of protocols because you don't know what you're trying to achieve. So for most of this, most of today's presentation, this is going to be the scenarios. It's a very classic scenario of secure communication. So like usually we say we have two parties, Alice and Bob, who want to communicate. And sorry? Why not Eve? Yeah, good question. So we have a third party that can either read, modify, do something to the communications between them. So I guess what I want you guys to think about is like, what is a real world situation where you have this kind of model, where you have two parties communicating and we want to keep the communication safe from somebody who's like either trying to read them or mess with them or something. So yeah.
The FBI.
Okay. Maybe like a more yeah.
ISP.
Your ISP, yeah, very good. So when you're accessing any website, right, you have to go through your ISP. So your ISP sees all of your network traffic, and they can modify any of your network traffic. They can do anything they want to your network traffic. And like perhaps you don't trust your ISP, right? Quite reasonable to do that. And like even if you do trust your ISP, like why do you want them to see/tamper with everything that you're doing? So that kind of comes to what are the actual security properties that we're trying to achieve. And the reason for talking about this is that you might just say that we want the communication to be secure, but we need to know what does secure actually mean. It could mean different things, and in different scenarios we might actually be concerned with different things. Like in some scenarios we might want some security properties, and maybe we explicitly don't want some security properties. So like a common way to think about these properties is what's called a CIA triad, a very convenient acronym. So C is confidentiality, which means secrecy. So the eavesdropper or the kind of man in the middle or whatever cannot read the messages that are being sent between Alice and Bob. So if you imagine, if the eavesdropper is your ISP, then like if you are accessing some website or something like this, then your ISP cannot see like maybe what you're putting into a form on that website that's getting sent to the website. Integrity means we want to make sure that the messages being exchanged between Alice and Bob cannot actually be tampered with, cannot be modified. So you could have a case where, like again, if you are accessing some website and like let's say you're accessing your bank, right, and you have a form to like transfer money from one account to another, maybe your ISP goes in and like changes the form response and has all of your money transferred to the ISP's account instead. So that would be a compromise of integrity. And in fact, it is possible to compromise integrity without compromising confidentiality, right? So you could have messages that are like encrypted or whatever between Alice and Bob, and like these messages could still be tampered with, and so Bob might take actions based on some tampered with messages. So like these are really separate properties. You can have some combination of them, and like sometimes you don't want some properties. Like maybe sometimes you don't want like explicit. You don't want confidentiality. You want whatever you're doing to be public for some reason, but you want integrity. Could be the case. Because like maybe you want to be transparent about something, right? Like maybe you're talking to somebody and like you want everybody to know exactly what you're saying, but you don't want them to be able to mess with what you're saying. So yes, there's a question here, like, can you think of a system where these properties are important? Like we have one example, which is your ISP and like you accessing the internet. Does anybody have any other ideas? Like where could these security properties be important to you? Like maybe one, maybe both, some combination of these. Yeah. Yeah, very good. So two general problem. So do you want to, I guess, walk us through what that is?
It's a thought experiment. Two war generals, right, living in two castles, and they have to communicate. There is a whatever military attack going on. They have to communicate with one general's trying to communicate with his fleet to attack the other general, right? And he has to be able to send them a message without another general knowing when they're going to attack. Right?
Sure.
If they know, then they can prepare. They don't want that, right?
Mhm.
But the general also needs to know that his fleet got the message, so that if he's expecting them to attack and they don't attack, bad things happen, right?
Yeah. Very good. So actually, kind of part of that is actually the third property, right? Availability. Like the property that the message actually reaches the other person. That is that's a separate property. Because you could have a situation where you have Alice and Bob communicating and like Eve or Mallory or whoever just drops every message, just doesn't send it, right? Or like your ISP just refuses to give you network service. So the fact that messages are actually being sent and you know that they're being sent is actually another different property. And I guess the generals example is kind of interesting because the study of cryptography actually started really with like military settings because it was important to exchange messages in secret. Okay, so threat model. So this is basically what can the attacker do? So one threat model is a passive attacker, also called Eve for eavesdropper. And what such an attacker can do is they can see the messages that you're exchanging with somebody else, but they cannot tamper with them. And I guess, can somebody think of like what is a situation where you could have such an attacker? So they cannot actually, like the ISP, right? They can mess with any message that you send. You can just choose not to send them. Yeah.
I assume just like Starbucks lurker. Somebody like you're both connected to Starbucks Wi-Fi, they can see traffic, but
Sure. Yeah, that's fair. Yeah, they can see anything that you're doing, but maybe not so easily tamper with it. And then like the more powerful attacker is a man-in-the-middle attacker or an active adversary called Mallory because malicious is kind of where that comes from. And this kind of attacker can modify any message. They can also just refuse to send messages. Like they can do anything they want. And of course, they can see messages. So they're strictly a more powerful adversary than an eavesdropper. And there's like this third case, which is actually very interesting. And like we probably won't talk about it today, but it's kind of a very, very new and exciting area in cryptography, which is what if the parties themselves are not trusting each other? Like you are communicating with Bob, but you don't even trust Bob. So like maybe you only trust them to a small extent where like you want them to learn something, but not everything or something like this. And actually there's like a whole area of cryptography called multi-party computation and like other like zero knowledge proofs and things like that, which kind of have this kind of model where parties want to be able to somehow collaborate, but they don't even trust each other. But they still like to do some kind of collaboration. Okay, so how are we going to achieve these security properties? At least today, it's going to be using cryptography, which is like the kind of real essence of it is that the security is provable. You can prove that whatever you design is actually secure by like a mathematical proof. And this is different from if you just design some like operating system, like security measures, like a stack canary or like ASLR, if you've heard of these kinds of things, or like you have some permissions or things like that. Because with all of those, it's really hard to kind of prove mathematically that what you're doing is secure. So like the real important part here is that we want to prove the security of what we are doing. And kind of as a result, like this is maybe a little bit unfortunate, but this is my opinion that like if you want to really do this stuff, then you should know the math. Because like ultimately we want to reason about things formally in terms of proofs and like try to argue formally why things are secure. Like you don't have to obviously understand the details of each and everything that you are dealing with, but like you should be comfortable enough with formal reasoning that you can actually kind of argue formally why things are secure. So like if you're really interested in this area, then I would suggest, I guess, doing math, like taking math classes or something. Okay, so we will now look at some kind of specific cryptographic protocols or cryptographic primitives that you can use to build protocols. But before that, does anybody have any questions? Okay, very good. So I guess the first kind of area of cryptography we'll look at is symmetric cryptography. So in this setting, Alice and Bob, like the important part is that Alice and Bob have a shared secret. So what this means is that they both share some value that is only known to both of them. Nobody else knows this value. And what they would like to do is that based on the shared value, they would like to communicate securely, and then they would like to achieve integrity and all of these properties. So it's actually, you can actually prove that like if there's no shared secret, there's no way to achieve any of these properties. Because if you think about it, if there's no shared secret, then like any attacker has exactly the same amount of information as Bob, right? If Alice is sending a message, there's no secret. So there has to be some secret. And in this case, the secret is shared by both Alice and Bob. And like there's a very natural question, which is like, how did the secret actually, get shared? Like if we are, if the whole problem we are trying to solve is that Alice and Bob cannot communicate securely, and like we need some way for them to be able to do this. And now we are saying that somehow they managed to get a shared secret. Like, how did this happen? And my answer is that like, don't worry about it for now. But we will see a technique how to achieve this. Or like you might say that they met in advance or something. Okay, so the first primitive is symmetric encryption. So this is, I think, the most intuitive primitive. This basically says that if I have a key and a message, using this NC operation, I can produce what is called a ciphertext, which is like the encrypted message. Given the same key in the ciphertext, I get the message. So like the important part is that it's the same key being used for encryption and decryption, which is what makes this symmetric cryptography. So like Alice can maybe use the key to encrypt some arbitrary message. The C will get sent over the network or whatever to Bob. Bob can decrypt it, and he gets back M. And like the security property, I guess you can read this if you want. This is like the kind of formal definition of what security actually means for this, because like again, it's important to really formally define what we mean when we say that the encryption is secure, because many hundreds of years of experience have shown that if you design systems that like where your security guarantees that like I tried to break it and I could not, then for sure somebody else will break it. So you need to like try to somehow argue what exactly your system satisfies in terms of security property. But just to summarize what the security property means, it means that if an adversary sees encryptions of any arbitrary messages that they can even control, it's like they can say, I want to encrypt this set of messages. Like it's an unrealistic scenario, but they can say, I want to encrypt this set of messages, and they can see the ciphertext of any arbitrary set of messages that they choose. They still learn absolutely no information about a new message. So it's like very strong security guarantee. Like in the real world, it means that they can see anything and like they still learn nothing in like very broad terms. So this is I guess a very important primitive. In practice, we use like block ciphers or stream ciphers to encrypt messages. It's important note is that even if like AES, for example, is a block cipher. Now, why is AES secure? Like, doesn't anybody have an answer? Why like we say AES is secure. Like, why is this true? Does anybody know? Yeah?
Because they said so.
Yeah, that's basically what it is. So AES is secure because a lot of people have tried to break it and nobody could succeed. So like you might ask, like, how is this different from just like making up any random cryptography? It's different because we only assume a small set of things. So we assume like the small primitive called AES that like very smart people all around the world have tried to break and they could not break it. And we can prove that other things are secure assuming that AES is secure. So at least we can get some assurance that like other protocols that we design are secure. If somebody breaks AES, then like it's all over basically. So like your protocol is like gone, but so is everything else. So I mean, a lot of effort has been put into trying to break AES, and like nobody succeeded. I think it's important to note that like these kind of ciphers, they can be, even if they're themselves secure, at least believed to be secure, you can combine them, you can use them in ways that are not secure. So this is an example of AES ECB, like favorite insecure mode of AES. So AES is a block cipher. It encrypts a block of input at a time. So if you have like a very long input, then like one natural idea is, okay, I'm just going to break it up into a bunch of blocks and encrypt each one individually. And actually, this is completely broken, as you can see. So like this is Penguin Linux. This is encrypted Penguin. I guess kind of hard to see, but you can actually see the outlines of a penguin here. And that is very bad. This should look like just a random image. And the reason why this is broken is like many reasons, but one of them is that it's completely deterministic. The same input always leads to the same output. So like this set of pixels here and this set of pixels here will lead to the same output here. So you can kind of correlate what is going on. And it actually breaks the security property. Okay, so this is encryption. This does not achieve integrity. Yeah, that is my, you can do it. So, you know, you can imagine like if Alice, let's say you have like the general's problem, right? Like General 1 tells his army attack at 5 p.m. And what could happen is that somebody else, it's an encrypted message, so somebody else cannot see what this message is, but maybe they can just mess around with some of the bits in it. And then when it gets decrypted, you get something completely different, right? Like maybe you decrypt it and like it now says attack at 8. And now, you know, the opposing army, like, or rather the army, at 5 o'clock, nothing happens. The general thinks the army is going to attack, like maybe he shows up and like there's nobody, right? So even if you have encryption and like confidentiality, you may still not have integrity. You may, your messages can still be tampered with. So to solve this problem, we have this idea of message authentication codes, which is basically a tag that you can associate with a message. So again, like it uses the secret key. So it says that given my secret key and a message, I can produce a tag. And this tag kind of goes along with this message. Again, think of it as like a seal that you put on the message. Like if you have a, like a, I don't know, like a bottle of like pills or something, it has a seal on it, right? To make sure that nobody can tamper with it. And the check function says that given a message and a tag, I can check is this tag actually valid. So if somebody tried to mess with my message, then actually the check will fail, is kind of the idea, because now the tag is no longer valid. And the security property of this, this system is that if somebody messes with my message, then they have no way to make up a tag that is valid without knowing the secret key. If somebody like tries to flip some bits in the message, the tag is now invalid. They cannot kind of manipulate the tag to make it valid. Okay, so any questions? Yeah.
Just like the stuff that they do with like again PGP public key.
Yeah. So that's a good question. So that is actually public key cryptography, which we will talk about in 2 slides. But yeah, so this stuff is symmetric key, which means that the 2 parties share the same secret, right? But like PGP public key, like if you imagine, yeah, exactly, right? Like you have a public component that everybody knows. Okay, so if you combine these 2, if you combine symmetric encryption and message authentication codes kind of in the right way, and there's wrong ways to combine them. If you combine them in the right way, you get this thing called authenticated encryption, which is like the gold standard of symmetric cryptography. What this gives you is basically, Alice can send messages to Bob. Nobody can read these messages and nobody can tamper with these messages. So it's basically like as, I guess, perfect as you can make it. They can still choose to drop the messages. Like messages may never actually reach Bob. But that is not really a cryptography problem, right? Because what can you do to stop that? Like if somebody cuts the network cable, then like nothing mathematicians can do to fix that problem. That is the problem of the systems people. So like you make your cable stronger, I guess. But ultimately there's no way to achieve availability necessarily with just crypto. And this is usually what you should use. Like if you want a secure communication between two parties, then usually you should use this because it creates this idea of a secure channel, which is you can pretend as if the parties are actually talking in private. Because to everybody else, it is as good as if the parties are talking in private because nobody can see any messages, nobody can tamper with any messages. Best they can do is just drop messages, but that's inevitable. So one way to achieve this is you combine like symmetric encryption and message authentication codes. There's also like specialized kind of encryption algorithms that give you both in one, like AES GCM is like Galois counter mode of ACM, but like not important of AES, but not important. You can just plug these in, like pretend that they work, right? Like as a protocol designer, you don't need to really worry about how is all of this actually implemented. You just need to know what is the security property it is giving me, and like how can I use it. So yeah, questions? Okay. Okay, so now asymmetric cryptography. So the big kind of question was, how did Alice and Bob get a shared key, right? Like seems kind of stupid that we are basing our secure communication on the assumption that there was secure communication in the past. Like that does not seem like a very good design. So to maybe motivate why we need this, we might have a situation where I want to send a message to you, but I have never actually met you before. So I have had no chance to exchange any kind of secret key with you. Or maybe you want to send me a message and you have never met me before. So if we have this kind of scenario, then like symmetric cryptography is not going to work, right? Because how do I get a symmetric key? I cannot just send you the symmetric key because now everybody knows the symmetric key. And like it's not secret anymore. So to solve this problem, we can use asymmetric cryptography. So in asymmetric cryptography, the idea is that every party, every like person has two keys. They have a pair of keys. They have a public key, which everybody knows, and they have a private key, which only they know. And these are not just like random. Like these have to be kind of generated together, so they kind of fit together. But this is kind of the setup. And the idea is that the public key is just published to the whole world, and the private key you keep with yourself. So using this, we can get, for example, asymmetric encryption, where the idea is that the encryption happens with the public key, right? And the decryption happens with SK, which is the secret key. And what this means is that anybody can actually encrypt a message, right? Because the public key is completely broadcast to the whole world. So like if you want to send me messages, right, what I can do is I can, like on my laptop, wherever it's in my bag, but I can generate a public key and a private key. I can write down my public key on the board, and you can use my public key to send me messages, and only I will be able to read them, right? And we have maybe never actually exchanged. Like I could write it on the board and like leave, right? And then you could come in later and you could send me a message on Discord, and like I would still be able to read it, even though we never actually met. Yeah.
Is the infrastructure the public key to create a message that people? I guess that's not authentication.
So I guess what property are you? So you want
Can
it?
you use your private key
Yeah,
to
yeah.
encrypt a message
Yeah.
such that the public key decrypts it,
Uh-huh.
and because they know that's the case,
Yeah.
only you could have written the message.
Yeah. So you're kind of getting at like a digital signature almost. And yes, kind of at a high level, that is the idea that you can achieve. Like it's the next slide actually, but it turns out that like if you just take any random public key scheme and like try to do this, it's not necessarily secure.
Ensure that it's like encrypted.
Yeah, I don't actually know what the property is, but well, there was actually, I wrote a false ETF problem where we had like RSA signatures, and like RSA encryption is secure, like to do it this way. But if you actually do what you suggest and you just like invert the encryption, then actually it's not secure. And you have to do like one additional thing, like you have to, like the details that you have to hash the message before you sign it. Well, anyway, kind of at a high level, you're correct that you can do this. The details, like you cannot just kind of plug this in directly. But yeah, so this is asymmetric encryption. And the next thing is digital signatures. So asymmetric encryption gives you confidentiality, right? Like you can now send messages in secret, but we still don't have any way to get integrity, right? Like I could, I write my public key on the board or something like this, and you try to send me a message, and then somebody intercepts this message and like messes with it. So like, what do we do? So to solve this problem, we have digital signatures, where the idea is that it's kind of like a real signature, like right? Like if I have a document and I sign it, then like the point is that like I endorse this document. Like nobody can forge my signature, but anybody can check my signature, right? That's supposed to be the point. So the signing happens with the secret key. So only the person who has the secret key can actually sign a message, but anybody can verify the signature. So because everybody has the public key. So I guess my question is like, how is this different from message authentication codes? Like, why is this scheme of ensuring integrity different from message authentication codes? Because like even here, if you don't have the secret key, the point is that you cannot make up a signature. Yeah.
In like the other one,
Yeah.
only the person you sent the message to could verify that the message was authenticated.
Yeah, that's exactly right. So with message authentication codes, it's symmetric key. So like only two parties, right, both have the shared key, and they can verify each other's messages, but nobody else can verify them. Here, the idea is that I can sign something and everybody can verify it. So it's a different, slightly different use case. And yeah, the security property is like similar, that if you don't have the security key, or sorry, if you don't have the secret key, then you cannot make up a signature for any like message of your choice. But it is worth saying that if you already have a signed message from somebody else, then you can just forward that to people, right? And that is still a valid signature. So like, is that a problem? I don't know, maybe. Exactly. It depends. Like it completely depends on the threat model and the situation, right? Like maybe you don't want to be able to take these signed messages and start forwarding them to people, and like they believe these messages are actually coming from the real person, which they like kind of are actually. Yeah, so question is, can you think of a kind of real world case where we need this primitive? Yeah.
I assume Bitcoin, both ways is where.
So what are we exactly using it for in Bitcoin?
This is basically just me recreating the Free Blue and Brown video,
Sure.
but it's like,
Because I don't know actually, like why this would
yeah,
be.
so Bitcoin, you're maintaining a ledger, right?
Yeah.
And then everybody's trying to, you need to verify that everybody's doing something good with the ledger. Nobody's modifying anybody else's.
Sure. Yeah, that's fair. Another case actually where we need this. Oh yeah. Okay. Well, so okay, there's like an interesting thing there. Like, DocuSign is not a digital signature. Like, they might call it a digital signature, but it's not.
Like the signing thing where they like do digitally sign certificates.
Okay.
Yeah, I had to get like a digitally signed certificate.
So did you have to like generate a key pair?
Yep.
Okay, yeah. Then it's yeah.
Like already passed.
Sure, yeah. If there's a key pair, then yes, that is exactly what it is. Or like, you have like PGP, you can sign things with it. But yeah, DocuSign is, I guess you can think of it in like as being analogous to a digital signature, in which like somehow your signature on the document like proves that it is from you and anybody else can check it, but it's like not actually this. Exactly. Yeah.
This is like HTTPS certificates. You have to like.
Yeah.
That they have to prove that they signed the thing.
Yes.
You have to know that they did it.
Yeah, very good. So a certificate uses signature, and actually, is there a slide on certificates? I might have forgotten that slide. But yeah, so what a certificate is a signed public key. So it's like a certificate is saying that like my public key is such and such, signed by Min. And if you trust Min, then you can trust that this is indeed my public key. So it's like that is the idea. But yeah, yes, a question? Did you have a question? Yeah. Okay, sorry. Okay, so right, so we have some algorithms by which we can get this stuff. So it's like RSA, elliptic curves. Like usually people use elliptic curves for various reasons. Like it's not actually important, but like again with this stuff, the point is that like no need to know what an elliptic curve is. You should know that it gives you these security properties, and like you should know exactly what security properties it gives you. But like you don't need to know what exactly is going on with like the math details. Like if you like math, then I guess you can read about it. Like elliptic curves are actually pretty cool. Okay, so now we have this idea of key exchange, which is I will finally answer the question of how do you get a shared secret. And the idea is you can actually use asymmetric cryptography to get a shared secret. So one very there's like Diffie-Hellman, but actually a very simple way to do it is like, let us say I want to send Min a secret key, or I want to get a shared secret with Min. What I can do is if I know his public key, I can generate some random key. I will encrypt this with Min's public key. I will sign it with my own public key, and I will send it to him. And now he can decrypt it. He can get the secret. He can verify it came from me. So now we have a shared secret. Right? So this is one way you can get a shared secret using asymmetric encryption. And there's also a Diffie-Hellman key exchange where it's kind of symmetric from both. Yes.
I was gonna say,
Yeah.
does anyone spot issue with like the method you described for sending the shared secret? Yeah. I mean, if anyone wants to answer it.
Like you have to trust the public key that was used to sign it is actually Manny's.
Yeah, so like he has to somehow trust a public key that's supposedly on our internet that does in fact belong to him. And so if there's a malicious attacker that intercepts is receiving of my public key, the attacker can change it to their public key, and now he's just sending secrets to the attacker.
Yep. Yeah, exactly. And this is actually even a problem with Diffie-Hellman. Like with any public key system, this is a problem because like the whole point is that you're using the public key to either send somebody a message or verify it. But like, how do you actually trust that this is this person's public key, right? Like if there's a website where it just says that Min's public key is like this, how do I know this website has not been hacked by somebody, right? And it's actually a very hard question. And it is actually an unsolvable question by crypto. Like you can do certificates, right? A certificate is just saying that somebody else will say that this is in fact Min's public key, or this is in fact my public key, signed by somebody else, like signed by Juniper, let's say. But now the whole problem is to verify the certificate. I need to know Juniper's public key. So it like only shifts the problem to a different party. So this is not a problem you can solve with cryptography. Like ultimately, you just have to know somebody's public key. And like your browser like hard codes the public key of certain like certificate authorities. And from there, you can get this kind of chain of trust to any given website. But like I think it's important to know that this problem of, do I trust that this is this person's public key is unsolvable by cryptography. You cannot solve it. Okay, so this is Diffie-Hellman. Like details are not important, but it's like each party has a secret key and a public key. They exchange some messages, and now they have a shared secret. And again, it's the same problem, right? Like if you have somebody sitting in the middle who's like tampering with the messages that are being sent, then you lose the security. Yeah, so here is man in the middle attack. Somebody can sit in the middle and they can basically pretend to be each party to the other party. And if we have no verification of public keys going on, then this is a big problem. So yeah, I guess you can look at the details later if you're interested. But yeah, so certificate is a signed public key. It basically says like there's a bunch of other information like validity and country and address and so forth. But the most important parts are that like this person like Mario Rossi has this public key signed by a certificate authority. So it like ties those two together. And if you trust the certificate authority, then you can trust this whole thing. Okay, hash functions we will actually skip due to time. Yeah, so now actually we are going to look at ECTF 2025 scenario and like try to think about how can we actually use these primitives to design a protocol. But like before that, I'm going to say that we have talked about some kinds of attacks. Like we have talked about breaking confidentiality by just like reading some messages, breaking integrity by manipulating or tampering with messages. But there's kind of a lot more to this field. So, one example is this thing called a replay attack. So has anybody heard of what a replay attack is? Yeah. Oh, sorry. Okay, replay attack. Yes.
I mean, I assume it's just, even if you can't change what somebody's message is, if you just tell them, if you tell the other party the same message over and over, you do stuff.
Yeah, exactly. So, there's like a very classic example, which is like, suppose you have like your car keys, right, that unlock your car. And maybe the way like the person designing this car like cares a lot about security. So they made some system where, the car key has a private key and like the corresponding car has the public key kind of hard coded into the car. And the car key generates a message, signs it with the private key, sends it to the car verifies it, like everybody's happy. Nobody else can, like a different key cannot unlock the same car, et cetera, right? So what is the problem with this system? Can anybody think of a problem with the system? So I have a car key that contains a private key. The car key will generate a message saying like unlock. It will sign this message, maybe even encrypt it or whatever, with its own secret key. The car knows the public key of like the key fob, and the car verifies, okay, it's telling me to unlock, I will unlock. So is there actually a problem with this scheme? Yeah? Yeah, exactly, right? So what somebody can do is like, as I'm sending the signal to my car, they can have some like radio listener. They record this message that I'm sending, and now they can just replay this message to my car and it will unlock, right? Because it is a valid message. And they have not broken confidentiality. Maybe the message is encrypted. They cannot see what is going on in the message. They haven't really broken integrity either, at least as far as the message is concerned, because they are not tampering with it. They have broken the integrity of kind of the whole system, but like the cryptography is still working as expected. So there may be a case where you use the correct cryptographic techniques, but you can have these kinds of issues. And then maybe you need some more ideas on how to fix this. Like, does anybody know what is actually a way to solve this problem? Yeah.
Proper IDA.
So what do you want to ID?
Maybe like the person who is giving this key also has to give some like unique identification code that changes like every like 5-10 minutes.
Oh, sure. Yeah. So I mean that's right. Yeah.
So like you sort of like a timestamp.
Yeah, timestamp. Yeah, very good. So what is common among all of these techniques is that like you somehow need to change the message that is being sent each time, right? And you need to change it in such a way that like if you try to send an old message back, it doesn't work. So one approach is that you encode the timestamp, like the current time, into the message, and if the car somehow knows the current time, then like they can check the current time. Like you can have some ID that changes every so often, or something like this. But anyway, like these, I guess, ideas that we are coming up with, like they are kind of not really cryptographic primitives. They're kind of more higher level things in the protocol. Okay, and then the other question is, all of this time we've been assuming that the keys are actually secure. Like this is generally how cryptographers think, that you assume that all of the secrets are actually secret. And assuming all of this, you can make up a whole system. But in reality, this is maybe not such a good assumption, right? Maybe the keys could be somehow compromised, and it happens all the time. Maybe some of the keys are compromised, but not all of them. So it may be necessary to try to design a system where, maybe if like partially some of the keys are compromised, then you're still safe to some extent. Like maybe, you don't want to have like one master key for your entire system that like if somebody steals this master key, it's all over. Maybe you have some different keys for different things, so that if somebody like maybe attacks one of your servers that contains one key, they steal that key, at least some other things are safe. So yes, these are some kind of ideas that are somewhat unrelated. Yeah.
An example of this was the Spring ECTF,
Yeah.
where they did the binary tree thing, but I don't exactly remember what it was. Could you actually explain that? Because I actually don't remember. All I remember is a binary tree, and you could only get the frames.
Sure. Yeah, we are actually going to do this now.
Oh.
So yeah, but that's a very good point. And like we also had this idea that we are going to have different keys for different channels, or like things like that. So you try to somehow finely scope what your keys are doing. And this is just like generally a thing that you do in computer security, which is that even on like operating system security, you usually it's a bad idea to have like one super user who can do everything. And like the only privilege levels you have are like either you can do nothing or you can do everything. So it's maybe a bad idea, right? You should maybe have some more finely scoped permissions. So it's like the same kind of principle. Okay, so now for the rest of the, I guess, 15 minutes, we will walk through ECTF 2025, where we had to design a crypto protocol. And actually, what is interesting about this protocol this year is that if you did it right, then your system was provably unbreakable by any means. Like the attacker can do literally anything they want. They can have full control over the hardware. They can run any code they want on the hardware. Like the hardware may as well belong to them. And still they cannot break any of the security properties. And this is all resting on the cryptography that was being used. Now, unfortunately, we did not come up with this. So our system got broken by CMU. But a number of teams were able to come up with this, and like it was just hopeless to try to attack their systems because the only way you can break their system is like if you break AES or something, and like you're definitely not going to break AES. Okay, so I guess just for a summary, we had in ECTF 2025, we had this kind of system. We had this uplink idea where we generate frames, the satellite TV system, I guess I should say. So this generates some frames. You don't have to worry about, I guess, all the things that are in black, actually, because those are just made up. Really what we care about is we have this encoder that generates frames, and we have a decoder that kind of decrypts frames and shows you the frames. So you can imagine the encoder is sitting at like the TV station or whatever, and your decoder is sitting at your TV, and it's sending you frames, and you can decrypt them. And I'm actually going to open up the MITRE guidelines. So I guess we will like heavily simplify actually what is going on here, just for time reasons. But yeah, so what this is basically saying is that to like deploy such a system, at the time of deployment, you can have these kind of global secrets. So once, or sorry, not even at the time of deployment. Once for your entire system, you can have a set of global secrets. Like maybe you fix these in your design in your factory. Then for each deployment, you can generate, based on these global secrets, you can generate some more secrets that you can use. But actually, the question of multiple deployments is like, for sure it was not actually even relevant. So we just assume there's one deployment. Okay, and then we had this idea of subscriptions, where the idea is that if I want to read frames from a given channel, I should have a subscription to this channel. So actually, for our purposes, like to simplify, we will assume we only have exactly one channel in our entire system. So we're like TV only has one channel. We can either be subscribed to it or not. If you're not subscribed to it, then we should not be able to read anything from this channel. If we are subscribed to it, then we should be able to read stuff from it. Okay, and like there was the whole timestamps idea, which also we will ignore. So subscription just lets you read everything, we'll say. In reality, there was this kind of interesting thing where subscription can only be for a limited period of time, but we will ignore that. But what we will consider is that there's actually many such systems. Like every team has such a system. And if I hold a subscription to one of them, then I should not be able to read frames from a different team's system. Okay, so yeah, this is kind of the idea. We can mostly ignore this stuff. So like this is the encoder which generates frames. It can take these secrets. We will ignore timestamp. There's a frame and a channel number. We will assume we only have one channel, and you get an encoded frame. And given an encoded frame, the decoder can actually decode the frame. And you have the subscription update idea where you can register a subscription. And the decoder was actually implemented on the hardware, and all teams had access to it. The encoder was sitting in the cloud in MITRE's infrastructure. So you could not really see that code or mess with that code, but you had physical access to the decoder. Okay, so this is the idea. So we will assume a very simple scenario at first where you have physical access to this decoder that was somehow generated at the time the system was deployed. You may or may not have a subscription to a channel or to the only channel for a given team. If you have a subscription, you should be able to read the frames. If you don't have a subscription, you should not be able to read the frames. So for now, let's only imagine this kind of attack scenario. So I guess just like open, this is kind of very vague, but like open question on what kind of cryptographic scheme can we try to design for this to achieve this security property. I mean, so if you have any questions about exactly what I'm trying to say, then please ask me, because like I made this up. Like this is not the official challenge had a very more complicated and like maybe more specific set of requirements, and I'm trying to just like simplify it, what's going on. But if anything is like unclear, then yeah, please ask me. Like, does anybody have any ideas for, what we are allowed to have one set of secrets that are generated when the system is deployed, and we can put these secrets in the encoder. We can also put these secrets in the decoder. That should be a hint. Yeah.
One set of encryptions initiate the communication, start the subscription.
Oh, yeah, good question. So the subscription actually happens like locally. So subscription is like just a file, and you can just like send, like you can just connect the decoder to your computer and like you can say, okay, subscribe to this file. So the communication just happens kind of directly. But you're right in the sense that maybe we want some like degree of authenticity on the subscription, right? Like people should not be able to make up subscriptions for a particular channel. Yeah.
Missing here. What if a subscription is updated while the code is not as powerful?
We will not worry about that. So we are not concerned with like really correctness here. It's more just like security. So like imagine like the whole thing is actually working perfectly. The decoder is just sitting online.
I'm just saying that because subscription must be stored for the system.
Yeah. Just ignore anything over here. Actually, I will change this to like maybe just this, because I have heavily simplified what is going on here. So and we are not concerned with like the actual hardware implementation, like implementation in code of any of these things. Like we're just trying to think about what kind of protocol can we come up with. So yeah, ideas. So yes. Sure.
So you make a subscription. The key, you could have like separate keys for separate subscriptions, but you have like symmetric.
Yeah. So is your symmetric encryption actually protecting the frames? Is that the idea? Yeah. Very good. So yeah, probably maybe we want some symmetric encryption to protect the frames, right? Because the idea of this is supposed to be that I can just get a bunch of frames on my computer, but I should not be able to actually decode or decrypt these frames unless I pass them through the decoder device. And the decoder device should only be able to decode them if it has a valid subscription. So maybe, yeah, so for sure we need to somehow encrypt the frames. Because if you don't encrypt the frames, then like, even without the decoder, you can read the frames. And like, I think at least one team did this. Multiple teams, yes. So multiple teams did not even encrypt their frames, or like did something to their frames which is not encryption, like they just somehow jumbled them around or something. So yeah, they're like completely broken. So yeah, okay, we need to encrypt the frames. We want to use symmetric encryption. So like the question is, we need some shared secret. Actually, in this case, we can actually kind of cheat, right? Because we have this global secrets at the time of deploying the system. We are like simultaneously deploying both the encoder and the decoder. So we can just put or we can just use the global secrets in kind of both of them. But then, there's actually also an interesting question, like, should the global secrets actually be in the decoder? Should the decoder contain a copy of the global secrets?
Yes.
Everybody gets that. So yeah. Yeah, very good. So, yeah, so if you actually did something where, you just said, okay, forget about subscriptions, right? I'm just going to put my secrets in the decoder, and they're just always sitting there. And all my subscription does is just flip a bit in the decoder saying, okay, I can decode now. So if I don't have a subscription, the decoder, which has the keys to decrypt the frames, in its internal logic will just say, okay, I refuse to decode frames, but it still has the keys, right? So if the decoder is like working properly, then this is probably fine. Right, but then that gets to your threat model. Like, what is your threat model? If people can mess with your decoder at like the hardware level, which we did, yeah, we had the physical. We could mess with it at the hardware level. Then maybe this is not a great idea. So maybe you don't put the keys in the decoder. So where do we put them? Yeah.
I mean, I would assume you only use them once at compile time, and then maybe but then you just have an encrypted secret in the decoder.
So I guess the kind of this comes to a question of a decoder that is not subscribed to the TV. We only have one channel, so I just call it the TV. The decoder that is not subscribed to a TV, should it actually even have the keys to decrypt any frames inside its memory? Like, it has no reason to, right? And if we put it, then that is just creating some more opportunities for an attacker to like somehow get them. So right, so how do we send it? Sorry? So think about what is actually like, what are we doing to a decoder that makes it encrypt or makes it be able to decrypt frames? Like, we have to subscribe, we have to send a subscription. And I said that we can just upload the subscription as a file. Like, I can just get a subscription, like, the TV, like tv.com, wherever, like Comcast, wherever they are. They will send me like a file. So
One that is only good for sending the subscription. And
okay. So I guess another question, like, does the subscription actually need to have confidentiality? Is there anything secret in the subscription? Like, or what is there that is secret in the subscription? Yes, maybe. So okay, let's come back.
Subscription contains the key that lets you decrypt the.
Yeah, very good. So yes, that's actually a very good idea. So why not put the key in the subscription? Right? Why not put the key that lets the decoder decrypt stuff into the subscription? So that
it is a file that we made.
it is a file that the designer of, like, we are the designer of the system.
So we decide what is.
We can put whatever we want in it. But like, other people could be attacking the system, right? So like, we better not just put like all of our secrets in it, because then they have access to them. But we can put what we want in it, yes. Like, the data format is completely up to us. So yes, you can put you can put keys in the subscription that will let you decrypt a certain channel, right? And that there's a question of like, should this key be actually secret? Because now if I am sending this key in the subscription, the attacker can now see this key, right, that I've just sent. Is that a problem actually?
Well, we also have decoder ID. So the decoder ID.
So forget about decoder ID. We only have one. I'm like very heavily simplifying this. We only have a single decoder. So I guess the very simplified model here is that like, we have this single channel on our TV. We can send like I can send you, if I made this TV system, I will send you a decoder like device, which you can do nothing with until I send you a subscription. But once I send you a subscription, I actually put a key inside that subscription file that lets you decrypt all the frames I'm sending you. So now, and the point is that you like open up some program that inserts this file into this device or copies this file into this device. But now you can see my key, right? The subscription I just sent you contains the key. You can see it now. Is this actually a problem? Should you be able to see it? Can you gain anything from seeing it?
If you can see the key, then you could send the key to someone else with a different encoder.
Very good. Yeah. So yeah, so that very good point. But actually, in this case, that was not part of the threat model. So the part of the threat model is that like, you cannot. I mean, yeah, like, well, I mean, that would be like cheating. If you stole somebody's key and like send it to a different team, then like, that is cheating. But yeah, let's say it's only you. I'm designing the system. I only care, can you break the system or not? I don't care who else you're sending my keys to. But you're very correct that like, in maybe a real system, this is a bad idea. But again, maybe in a real system, we might do something where I give everybody a different key somehow. So, something like that, maybe, yeah. So Actually, I think it's that, yeah.
So, as far as I understand, if you're given an authentic subscription
Yes.
from the actual company, if you have the key, it shouldn't be a problem since you should be able to read the decode the frames anyway.
Yeah, exactly. So it's actually no problem if you have the key, because you can, like, all that the key gives you is the ability to decrypt frames sent from the encoder. But you could do that anyway if you have the subscription, because you would just subscribe your decoder to this channel, and now the decoder is just decoding all the frames for you. So like, what is the difference if the decoder is decoding or you're decoding it yourself based on the key? It's like, from a security point of view, there's really no difference. So actually, in this very simplified scenario, it is fine for you to have the key, right? No problem. But like, you're right that if you're concerned with like different people using the system, then like maybe we don't want to do this, because now people can share their keys with each other. Like, people like share Netflix passwords, kind of similar issue, right? So okay, so that is like a very basic. Okay, how much time do we have? We might be out of time. Okay, we have like 1 minute, but we'll add like one small element of complexity to this, which is that we now have different decoder IDs. So for a given deployment, there's still a single encoder, but there's more than one decoder. So like, I have my TV system, and I actually manufacture 5 decoders. I give these to like 5 people in the room. And if I give one of you a subscription, the subscription will contain within it the decoder ID that it's allowing to subscribe, and somebody else should not be able to use this subscription to actually start decoding frames. So like, this current idea of just put the key in the subscription stops working, right? Because if all that is in the subscription is the key, then like anybody can use it now. Yeah.
Well, if the encoder knows which decoder is subscribing to it, then all you need to do is make the decoder ID like non-trivial, so that you can encode the key that you're sending with the decoder ID.
So you're saying I'm going to now encrypt the key,
Or add it to the encryption. So you can have 2 keys. One key is the decoder ID, the other key is the subscription.
but what if I know somebody's decoder ID? Like, a decoder ID should not really be a piece of secret information, right? Like that, it's not really very good.
It's not secret. Like, if anybody can just take somebody else's decoder ID, what we really do to stop them from pretending to be each other?
So I guess let me kind of make this a little bit more specific. So like, the scenario that you're in is that you have your own decoder with a certain ID, your choice. And I give you a subscription for a different decoder ID. And the security property that we want is that you should be able to do nothing with the subscription. But you know both the decoder IDs. You know the decoder ID of your own device, and you know the decoder ID of the subscription I just gave you. Like, I think I may be misremembering, right? I think that this was the scenario. Yeah. So it is certainly possible to get security in this case.
I guess the thing that makes the most sense is if you have a subscription, that should give you the right to request access to the channel. And then maybe you sign that request with your, I guess that would work with someone else. If the decoder has a private key.
But we don't have global secrets, so we can't have it right.
And I guess also, like, in this particular scenario, there is no communication like the other way. Like, the decoder cannot talk to the encoder.
So you have a satellite that's communicating one way.
Yeah. So I mean, this is like maybe a kind of unrealistic constraint, but that is the constraint that we have.
You build the decoder ID, what is stopping you from just making a decoder with that ID? And from just having a decoder with that?
I don't know. What is so okay? So let's get back to this. What do you not know in this whole scenario? Like, what is it? Like, what is the piece of information that you actually don't know? Yeah, you don't know like the global secret, right? Like, that is the only thing really that you don't know. If you know the global secret, it's like all over. Like there's no security. But there is this one thing that you don't know. You don't know the global secret. So like, the question is based on the fact, like, as me as a system designer, based on the fact I know that you don't know the global secret. At least I'll assume that you don't know the global secret. Based on this fact, can I actually achieve any kind of security here?
No, because everything else is known, so as long as one person, given all the constraints you described, as long as one person can decode frames, then anybody can decode frames.
Can they? I don't
Well,
know.
if you know everything about the person who's decoding the frames, then.
But you don't know the global secret. So you know their decoder ID.
The decoder does not have the global secret.
So that was from earlier. That was one of the introduction to this, where we're saying, should the decoder have the secret decoder stored on the device?
Okay.
Right. So that's in the subscription concept. Because we're introducing this concept of multiple devices, I think what we actually want to do is we need to have each device with its own unique.
Yeah.
So we're going to extend this where we now add some
But if the secrets of the device, we can just send them to a different device, and now it's.
So we assume like there's no cross communication. Yeah.
No, so this is very good point. This is very like manufacturing factory.
Oh, okay.
So like the subscription to decode frames is like sent to the customer, just loaded onto the device. When you can have some global secrets loaded on the device in the factory before it reaches the customer.
So we have the subscription key and the decoder unique. Is what you said.
No, we just encrypt the key that we put on the device, like when we send over the security key, with the key that we put on the device.
But then it needs to be decryptable by all decoders with the subscription, not just. Which I guess is that possible?
So the subscription is.
Whatever a device subscribes, send them the.
Yeah. The subscriptions are specific. Yeah.
We know which device we're sending it to because they requested
yeah,
to send. So now we just decrypt it with that device's key. If a different device does it, we just have to do this process again, which we'd have to do anyway in the first place.
Yeah, I think.
Track of all keys we send to devices.
So we have no state. That is like one of the hard parts of this challenge, that we can hold no states. Like everything has to happen at build time. The only thing we know is like what is the set of decoder IDs that we are generating. This we know at least.
And we also know that the specific timestamps of gaining and losing subscriptions, right? Or not.
You can, I guess you can say like we should be able to generate those based on the global secrets and the decoder IDs. So actually the answer is that this involves a primitive that you don't know about. It is called a key derivation function. And like your homework assignment is read our design document and like find the answer. No, like actually readers, like actually, yeah. We can send it.
The announcement.
Yeah.